So this is our last example for the mean value theorem. The problem statement is very similar to the last few videos. We're asked to determine whether the theorem applies. If so, find the x value is guaranteed to exist by the theorem for this particular function on this particular interval. That's our part A and that's our part B. And then we say, okay, if the theorem doesn't apply, modify this statement so that problem statement so the theorem does apply, then find the x values that are guaranteed to exist by the theorem in terms of m secant this time. So we're going to find them as a formula involving the slope of the secant line. Then we're going to graph the secant line and the tangent line, show that the lines have the same slope. In other words, if the lines are parallel, then they have the same slope. And if they have the same slope, then we found the x values that we're looking for. Again, we want the average rate of change to equal the instantaneous rate of change at a particular location. And that means that the tangent line and the secant line are parallel. So we've got this function y equals x to the 2/3. And we're on the interval from -4 to 6, or we're on the interval from 0 to 8. Now, the way I have a tendency to think about this is I think in terms of y equals the cube root of x, or y equals x to the 1/3. Kind of looks like this. It looks like an x cubed function, or a y equals x cubed function, but on its side. If I square that, I'm taking all of these y values and I'm squaring them, and I'm taking all of these y values, which happen to be negative, and I'm squaring them. So when I square those, what I end up with is something that looks like this. Kind of reminds me of a bird. Looks roughly like this. Because if I take x to the 1/3 and square it, we just multiply the 2 and the 1/3 and we get x to the 2/3. So that's our function. And on this first, for this first problem, we're interested in the function on the interval from -4 to 6. So at x equals -4, we're going to get some value, and x equals 6, we're going to get a different value. This is not to scale, of course. So we're here. We're just talking about this part of the function in the middle. Now, remember what the mean value theorem says. It says this: if the function is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then there exists at least one x value in the open interval from a to b, such that the instantaneous rate of change, that's the derivative at that particular x value, is equal to the average rate of change. So it's just the slope of the secant line that goes through the two endpoints of the function. When I look at this, I see it's obviously continuous because I can draw the graph without picking up my pen, but it's obviously not differentiable. Look at what happens at x equals 0. We end up with this little cusp. The slope as we approach x equals 0 from the left is negative, and then the slope as we, or excuse me, is it negative? Yes. And the slope as we approach x equals 0 from the right is clearly positive. So we're going to have a problem near x equals 0. So the mean value theorem does not apply. So let's write that down. I guess we could say that because the graph of y equals x to the 2/3 has a cusp at x equals 0. Alternatively, you could say y prime is the derivative with respect to x of that x to the 2/3. Take the derivative using the power rule. So you bring the exponent down, multiply by x to the 1 less power. 2/3 minus 1 is 2/3 minus 3/3. 2 minus 3 is -1, so we end up with a -1/3. Now remember, when we write that with positive exponents, we have to use this property. X to the -n is 1 over x to the same power but positive. So this x to the -1/3 is actually an x to the 1/3 in the denominator. So we end up with that. Now this is going to be undefined whenever that denominator is 0, and that denominator is 0 when x equals 0. So y prime exists and is fine, and it's nice and continuous as long as x is not 0. So y prime, let's say, is undefined when x equals 0. So y equals x to the 2/3 is not differentiable on the interval of interest. So the mean value theorem does not apply. So you actually have two options for talking about why the mean value theorem does not apply, but they're pretty much two different ways of looking at the exact same thing. The first one is to just look at the graph and say, look, it has a cusp there. The slope from the left and the slope from the right of 0 are two different signs. So there's no way that we have a well-defined tangent line at that location. So the function is not differentiable. Or alternatively, you can actually compute the derivative and say, when is that derivative well-defined? And say, well, this derivative is well-defined as long as x isn't equal to 0. So either way, it's not differentiable. We know it's not differentiable graphically because it looks like this. And then we know it's not differentiable algebraically because we know that this function is undefined when we plug in 0 in the denominator. So we say, okay, provided that that's the case, can we modify the problem statement so that the theorem does apply? And I think the answer is yes, because this function is nice and smooth and nice and continuous on any interval that does not include 0 on the interior. So I could go from 0 to 6. I could go from 0 to, well, not all the way to infinity, but from 0 to any finite number, and it would be fine, or from any finite number to the left of 0 to 0. So I can start anywhere and end at 0, or I can start at 0 and go to the right. Either one is fine, or I can start at any a value to the right of 0 and have a b value to the right of that a value. So basically, as long as that x equals 0 is not on the interior of our interval, the mean value theorem will apply. Function will be continuous, it will be differentiable, as long as it's not on the interior. And yes, because remember, where's our problem statement? Or not our problem statement, statement of the theorem. The function just has to be differentiable on the open interval from a to b. It doesn't have to be differentiable at the endpoints. Okay. So now we're going to find the x values guaranteed to exist by the theorem in terms of m secant. So we say on an appropriate interval. Well, actually, let's answer the question first. Can we modify the problem statement so that the mean value theorem applies? Yes. We can select an interval that does not include x equals 0 on its interior. Then y equals x to the 2/3 will be continuous and differentiable on that interval. Which implies that the mean value theorem applies. Okay. Now, in that case, the x values we're looking for are those that cause the derivative to be equal to the slope of the secant line on that interval. So we want m secant to be what it always is. It's just the function evaluated at b minus the function evaluated at a, just change in y, divided by change in x. And we want the derivative of this function to be equal to m secant. Y prime is the derivative of this, which we've already computed. We're going to set that equal to the slope of the secant line. Now, if I'm solving that for x, I want that x in the numerator, so I'm just going to take the reciprocal of both sides. I'll multiply by 2/3 on this side to get rid of the 3/2. That's legal as long as I do the same thing on the other side. And then I've got an x cube root of x, or x to the 1/3. Raise both sides to the 3rd power to get x by itself. So x is equal to 2/3 cubed, which is 8 divided by 27. 2 cubed is 8, 3 cubed is 27. Times 1 divided by the slope of the secant line cubed. Or if you prefer, you can write it as a single fraction. Now this x value is guaranteed to be on the interval from a to b as long as we are on an interval that does not include x equals 0 on its interior. So any interval is fine as long as 0 is not on the inside of it. It's okay if 0 is on the endpoints, just can't be on the inside. In that case, this is the x value that we're looking for. So let's explore this graphically on desmos.com. Okay, so here is the function y equals x to the 2/3 on the original interval from -4 to 6. So we see that the entire function is that sort of bird-shaped thing. And when we're just interested in that part between x equals -4 and 6. So we're interested in this highlighted part. We computed the derivative on paper. It was equal to that function. 2 divided by 3 times x to the 1/3 power. And if we compute the slope of the secant line, turns out to be approximately 0.078. And the equation of the secant line is just the y value at x equals a times the slope of the secant times x minus a. So change in y over change in x times change in x gives us change in y plus the original y is the new y value. And so we get that as the equation for the secant line. We say the mean value theorem should not apply on this interval because we've got this cusp here. We know that the derivative is undefined at x equals 0. Now, if I want to find the equation of the tangent line at any point, I'll just use y equals f of x naught plus the derivative at x naught, that's our slope, times x minus x naught. I'm gonna let x naught take values between a and b. So there's my point. Now, if I let my x values change, and I'm looking for a tangent line that's parallel to that secant line, I'm not gonna find one. All the slopes between x equals -4 and x equals 0 are negative. And then the slopes over here between x equals 0 and 6 are positive, but they're not steep enough. The x value that we got when we solved for x by setting x or y prime equal to the slope of the secant and then solving for x, that x value is x equals 619.39 approximately. So it's way outside of our interval. So there actually is an x value that gives us the right slope, but it's not on the interval of interest when we include that cusp. So if we go farther and farther away, all the way out to x equals 620 approximately, way out there, there is an x value where the slope of the tangent line is equal to the slope of the secant line. But again, it's not on the interval of interest. We just can't find one on the interval of interest if our interval includes that cusp. And so you say, okay, let's change it. Let's modify the problem statement. Instead of letting a and b equal -4 and 6, why don't we let a equal 0? If a equals 0, then let's let b equal, let's say 8, that's fine. Then we're right here. And let's change the y values as well. So we're right here. We say, okay, is there an x value on the interval that gives us the right slope? In this case, if x equals, or if a is equal to 0 and b is equal to 8, the slope of the secant is found using the same formula. We get a slope of a secant of 0.5 or 1/2, same thing. And we're looking for a particular tangent line that has a slope of 1/2. Well, the slope is given by f prime, evaluated at the x value. And I want that slope to be 1/2. You could just sort of move your slider around until you get a slope of 1/2. At approximately 2.37. it looks like our slope, our derivative is equal to about 0.5. But if we want the exact answer, then we can solve the equation. We can set f prime equal to 1/2 and solve for x. So we'll do that on paper. We've got slope of the secant. We know that that's 1/2. We can confirm that by doing the calculation ourselves. So I've got 8 to the 2/3 minus 0 to the 2/3, which is just 0, divided by 8 minus 0. And remember the 2/3 power is just the cube root of that expression squared, or the cube root of this expression and then squared. So x to the m over n in general is the nth root of x to the m, or you can call it, or you can think of it as the nth root of x raised to the m. Either one is fine. But when we evaluate this, we want to make the numbers smaller. So I'm actually going to use this one this time. So when I take 8 to the 2/3 power, what I'm really doing is I'm taking the cube root of 8, finding out what that number is, and then I'm squaring it. That number in the denominator becomes the index of the root. And that 2 can either go inside the radical or outside the radical. Either one is fine, but I want to make things smaller. So I'll say this is the cube root of 8 squared divided by 8. The cube root of 8 is 2. So I've got 2 squared, which is 4 divided by 8, or 1/2 for the slope of the secant. And I want the slope of the tangent to be equal to the slope of the secant. So that means I want y prime, which we've already calculated, to be 2 divided by 3 times x to the 1/3 to be equal to 1/2. We're going to set the slope of the tangent equal to the slope of the secant. That is equal to that. And then we just solve that equation. To do that, I'll take reciprocals of both sides because I want my x in the numerator. Let's multiply both sides by 2/3. Get rid of the 3/2. And then to isolate x, we're going to cube both sides. The x is 4 cubed, which is 64, divided by 3 cubed, which is 27. So that is the x value that gives us the right answer. At x equals 64 divided by 27. F prime of x is equal to the slope of the secant line, or the instantaneous rate of change is equal to the average rate of change on the particular interval of interest. So we'll let x naught equal that 64 divided by 27. Graph the tangent line there, and we can see that the tangent line and the secant line are parallel to each other. And if we want to be sure, we can actually see the slope of the secant from earlier was 1/2. And the derivative evaluated at x naught is also 1/2. So we found the right answer. In general, we can plot that point. And we can graph the tangent line there as well. All right. So that's that. There are more notes in here that were created as I was creating this graph. I think that's our last example. It's an example involving a cusp. So the mean value theorem doesn't apply when the function either fails to be continuous or it fails to be differentiable. This is an example of a function that fails to be differentiable on an interval. So we can modify it by excluding that point where the derivative is undefined, by either making it one of the endpoints or just not including it on the interval at all. When we're dealing with functions that have infinite discontinuities or vertical asymptotes, then we do what we did in the last video. We haven't looked at jump discontinuities or what's it called? Removable discontinuities, but the principle is pretty much the same. With removable discontinuities, it's possible that we could redefine the function. We could find a continuous extension of the function where everything is nice, everything is well-defined because the limit exists. Well, with jump discontinuities, I think we're going to have a problem as well. But that's it. That's it for the mean value theorem. Let me know if you have any questions. If you want me to make you a video, I'd be happy to do that.